We're almost ready to start talking about organic chemical reactions. But before we do, we need to have a set of tools to enable us to understand what's going on in these reactions. And the place that we're going to start with this is an energy diagram similar to the ones that you saw in general chemistry. So this is an energy diagram for a reaction that has more than one step. So you're probably familiar with seeing diagrams like this for just one-step reactions. This one involves multiple steps. And so the overall reaction would be taking us from the reactant side, A, to the product side, E. But within that reaction, we have these two steps. So going from A to C is step 1, we'll call it. And going from C to E is step 2. So step 1 is A to C, and step 2 is C to E. So these are what are called the elementary steps in the reaction. So we can add them together. When we do that, C appears on both sides, and so it cancels. And what we're left with is A going to E, which is the overall reaction. So for starters, what that tells us is that C is an intermediate. It's an intermediate because it's created in one elementary step of a reaction and consumed in another. Okay, so that takes care of C. Now let's look at some other quantities on the diagram. So we have a quantity of energy right here. So between A and this guy up here, B. And we have a similar quantity of energy going from C to D. You might remember that these are called activation energies. So we'll call this one E sub A 1, because it's the activation energy for step 1. And we'll call this one E sub A 2 for similar reasons. So the activation energy which is E sub A, is just the amount of energy that's required to get from the reactant of a step to what we call the transition state or the activated complex. Okay, so the transition state in chemistry is often abbreviated or symbolized with this double dagger, it's called. So like an equal sign with a slash through it. That refers to a transition state, or what you may have learned to call an activated complex. So the activation energy takes us from the reactant of a step to the transition state. So B and D are both transition states. So the activation energy is the energy required to get from the reactant of a step to the transition state. And so we can also say that B and D are transition states. Okay, some other quantities of energy here. We look at the difference in energy between A, which is the reactant, and E, which is the product or products, for the overall reaction. Then that difference in energy is going to be a delta H, or depending on what we're plotting, it could be a delta G. So over here on the left, I'll just say energy. That could be the enthalpy, or it could be the Gibbs free energy. So the diagram is a reflection of what's going on in each of the elementary steps of the reaction or of the chemical mechanism. So the mechanism. A chemical mechanism is just a step-by-step description of how a reaction is happening. So for example, on the first, or in the reaction up above, that's plotted up above in this diagram, in the first step, A is converted into C, which is an intermediate. Okay, so that could be that A fragments, maybe part of A breaks off, so a bond breaks, or it could be that something else, one of the reagents that you have in there, interacts with A and turns it into something else, so a bond forms. Okay, but whatever the case, whether it's a bond forming or a bond breaking, or a combination of those things happening, A is converted to C. So that's the first step. A would be the reactant of the step, and C is the product of the first step. In the second step, C is now the reactant, and E is the product. So the mechanism is telling us how this happens. Now, the mechanism and the way that we think about it is going to be related to what's called the rate law. Now, I've written an example of a rate law. The rate law, what we're interested in here, has to do with what's called the rate determining step, or the rate limiting step. In a diagram such as this one, the rate determining step we can pick out because it's the step that has the highest energy transition state. So if we go back up here and look, the step with the higher energy transition state is the first step because B is higher in energy than D. So in this example, it's step 1. The rate law for the overall reaction has to agree with the rate limiting step. So the rate law must agree with what's going on in the rate limiting step. So rate limiting, rate determining, totally interchangeable. Now let's bring in an equation that you remember from general chemistry, and that's the Arrhenius equation. The Arrhenius equation is going to relate the rate constant K. So remember that the rate of a chemical reaction is equal to the rate constant K times the concentration or concentrations of different things in the reaction. In this case, I'm just saying the concentration of A. Now from the Arrhenius equation, what we can see is that K and the activation energy are inversely proportional. Okay, so what does that mean? It means that the larger the activation energy, the larger the quantity of energy needed to get to the transition state, the smaller the rate constant. So a larger activation energy corresponds to a smaller rate constant, and the smaller the rate constant, remember that the rate constant is a proportionality constant. If the rate constant is smaller, the rate will be slower. So a smaller rate constant, K, corresponds to a slower rate of reaction, or a slower rate for that step. By contrast, a step with a smaller activation energy, so a smaller barrier, a smaller hill to climb, is going to have a larger rate constant and thus corresponds to a faster rate. Let's take a look at the key differences between transition states and intermediates. Okay, so we've talked a little bit about some of these already, but we're just going to put them all in one place. As well as fill in some ideas about transition states that we don't have at this point. Okay, so first of all, an intermediate is created in one elementary step of a mechanism and consumed in another. So created in one elementary step and consumed in another. By contrast, a transition state is a high energy point between the reactants and products of a single elementary step. Okay, what are the other differences? In an intermediate, all of the bonds are fully formed. But in a transition state, there's at least one bond that's partially formed. It's either in the process of forming or it's in the process of breaking, but you'll have at least one of those. So a transition state, in contrast, has at least one bond that's partially formed. And what that means is that the bond or bonds is or are in the process of forming or breaking. And the final difference between intermediates and transition states. An intermediate can be isolated and it can be observed. Now, that might not be for a very long time. So we can observe it, but maybe we can only observe it for a few seconds or a few nanoseconds even. But at least it's able to be observed through spectroscopy and other means. On the other hand, a transition state can't be isolated, and we can't observe it directly. So this is what we call not isolable, can't be directly observed. So the way that we figure out what the transition state structure looks like is by calculation, modeling, and comparing it to chemical species that it's related to in the same energy diagram. So we can make notes of that. We can determine or predict its structure by calculation or computer modeling. And our entry point for that, for making those calculations or doing that modeling, our starting point is by comparing to related chemical species. In the same diagram. Or reaction. Okay. Let's focus on certain types of intermediates. I'd like to go over with you the types of intermediates that you're most likely to see in organic chemistry. Okay, so there's three major types that we're going to run across. So let's talk about each of these. Carbocations. A carbocation is a structure that has a carbon with a positive charge. So let's draw a picture. Here's an example of a carbocation. The carbon that has the positive charge is sp2 hybridized. As such, it has 3 sp2 orbitals and 1 p orbital. The p orbital has nothing in it. It's empty. And that empty p orbital is going to be perpendicular to the plane formed by the sp2 orbitals. In this structure, if we were to count electrons, we would find that there's 6 electrons around the carbon that has the positive charge. So a carbocation is probably the most common intermediate you're going to see. Something called a radical, which we'll see from time to time, a radical has an atom with an unpaired electron. So let's look at an example of a radical. Okay, so that dot represents the unpaired electron. Now, the hybridization of the carbon in this case that has the unpaired electron is actually sp2. Now, it looks, because you have the 3 bonds and that 1 electron, it looks like you have 4 things, which you do. So you wouldn't be out in left field if you thought that that should be sp3. We happen to know that it's sp2 because of experiments that we've been able to do. So this one we know from experiment. The p orbital contains that single electron. And then again, if we were to count the electrons around the carbon with the unpaired electron, we'd come up with 7. So both carbocations and radicals have carbon atoms that are short an octet of electrons. And so for that reason, we can call these reactive intermediates electron deficient. Because they have carbons that lack full octets. Okay, a third type of reactive intermediate that you'll see more next semester is called a carbanion. A carbanion has a carbon with a negative charge. So let's just look at a structure of a carbanion. And that looks like so. Now let's focus in on carbocations, because we're going to see those more than any of the other intermediates. So what we're interested in is looking at the structural features that can stabilize carbocations. Now, it's important to notice that all carbocations, because they are reactive intermediates, are relatively unstable. But some are more stable than others, and so that's what we're going to try to sort out here. So let's start from that premise, that all carbocations are relatively unstable, but some are more stable than others. There are going to be 3 factors that we'll consider when we think about things that can stabilize carbocations. 2 of those we've seen, the third one is new. So the ones that we've seen are inductive effects and resonance, and the one that we haven't seen that we'll go over a little bit later is hyperconjugation. All three of these involve delocalizing electrons. When we delocalize electrons, it lowers their energy. And if we lower the energy of electrons, that lowers the energy of the structure they're contained in. Okay, so let's start with inductive effects. Now, the first thing we're going to do is draw a set of carbocations. And so let's get to doing that. So we'll have 4. In the first case, the carbon with the positive charge will have 3 methyl groups. In the second, it'll have 2 methyl groups and an H. In the third, 2 H's and a methyl group. And then finally, the last one, all H's. So before we get started analyzing the structures, let's look at a little bit of nomenclature or labeling. As it turns out, we can use the labels primary, secondary, and tertiary to describe carbocations. So we would be assessing the carbon with the positive charge and how many carbons it's attached to. So in the first example on the left, the carbon with the positive charge is attached to 3 other carbons. That makes this a tertiary carbocation. In the next example, the carbon with the positive charge is attached to 2 carbons, so it's a secondary carbocation. The third example, the carbon with a positive charge is attached to 1 carbon atom, so it's a primary carbocation. And then this last carbocation, where the carbon is just attached to H's, we call that a methyl cation. In an inductive effect, which we saw initially when we were thinking about acid-base chemistry, the electron delocalization that's going on occurs through sigma bonds. Now remember that alkyl groups are what we call electron donating or electron releasing, meaning that because carbons and hydrogens, which are the atoms that make up alkyl groups, because they're not very electronegative, they don't hold their electrons very tightly. So they're able to release electron density through sigma bonds towards some other point in the molecule. In these cases, the other point in the molecule that they're releasing electron density toward is the carbon with the positive charge. So in the case of the tertiary carbocation, we see that there are 3 alkyl groups that are able to do this, whereas for the secondary carbocation, there's only 2. In the primary carbocation, there's only 1, and the methyl carbocation, or the methyl cation, has none. So the more delocalization and the more donation of electron density toward the carbon with the positive charge, the more stable the cation, which means that a tertiary cation is the most stable, followed by a secondary, then primary, and then finally a methyl cation would be the least stable in this set. So to sum this up, more alkyl groups attached to the carbon with the positive charge means more electron delocalization, which results in a more stable structure. Now we can extrapolate this and generalize it and say that tertiary cations are going to always be more stable than secondary, which are more stable than primary, and all of those are more stable than methyl cations. Another effect we saw has to do with resonance stabilization. Now remember that resonance stabilization, the electron delocalization, is occurring through a pi system. So the places where this is going to matter would be in the cases of allylic and benzylic cations. So referring back to what we did with resonance, remember that when you have a double bond next to a positive charge, you can invoke a resonance move like the one that I've just drawn. And that's going to be similar to the situation you have with a benzylic cation. So a benzylic cation involves a positive charge on the carbon directly attached to the benzene ring. An allylic cation involves a positive charge on a carbon directly attached to a double bond. Okay. We also have more resonance contributors for the benzylic cation, but we've drawn those before, so we won't worry about that at this point. Let's look at the third feature, or the third factor that would stabilize carbocations. This is called hyperconjugation. First of all, let's define what that is. Hyperconjugation is the interaction of a filled orbital and an empty orbital within the same molecule. Now, in the case of carbocations, this is what you're going to look for. The empty orbital is always going to be a p orbital. So it's going to be an empty p orbital, and that's going to interact with a molecular orbital that's a bonding orbital. So in hyperconjugation, in the case of stabilizing a carbocation, the filled orbital is going to be a bonding molecular orbital that has electrons in it, and the empty orbital will be a p orbital. Okay, so let's look at where all of that stuff is going to show up. So here's an example of a carbocation. Now, as it's drawn on the left, it's in the plane of the paper, or the board, or the screen. We'll just say paper. Now, let's put in one of the carbon-hydrogen bonds coming off of a carbon that's next to the carbocation. Here's some more labeling for you. The carbon with the positive charge we call the alpha carbon. One bond away in any direction is called a beta carbon. So what we're looking at is the hydrogens that are attached to beta carbons. The bond between a beta carbon and a hydrogen is a carbon-hydrogen sigma bond. And as such, it's going to be associated with a CH sigma orbital and a CH sigma star. It's the CH sigma that contains the electrons. So CH sigma and CH sigma star. So every CH bond has these two molecular orbitals. The p orbital exists on the carbon with the positive charge. Now, if all of these bonds that I've drawn in, or that were already drawn in, are in the plane of the paper, the p orbital is perpendicular to that. So if we pull the structure out of the paper, and turn it so that it's perpendicular to the paper, then we're going to get a picture like the one shown to the right. So here is the MTP orbital. Notice that when we make the structure perpendicular to the page, then one of the methyl groups comes out towards us, the other one goes back. The molecular orbital that I highlighted in the structure on the left is going to be this one right here. So this is a CH sigma molecular orbital. It's a bonding orbital. Okay, so these two orbitals are going to interact. So there's going to be an interaction between the two. Now let's think about what that means for the electrons that are in that bonding orbital. So let's draw a little energy diagram. And so here is the CH sigma orbital. That has a pair of electrons. And then over here is the MTP orbital. When orbitals interact, they mix. They mix in phase and out of phase. The electrons that started out in the CH sigma orbital are going to come down to a new lower energy level. So they have been stabilized by whatever this quantity of energy is, delta E. So what we can say about this is that the interaction of an empty orbital and a filled orbital stabilizes a pair of electrons. Stabilizes, meaning brings down the energy of. And remember, when you stabilize electrons, you stabilize the structure they're in. Hyperconjugation always involves an MTP orbital and a bonding orbital that's associated with a neighboring, that is to say, a beta carbon. So hyperconjugation always involves an MTP orbital and a bonding orbital associated with an adjacent carbon. That would be a beta carbon. Now, if we go back up to this structure, I only drew in one of the carbon-hydrogen bonds coming off of one of those beta carbons. But there's two others, which means that there's two other, from that beta carbon, there are two other possibilities for a filled orbital to overlap with the MTP orbital. Remember that each of these bonds is rotating. And we'll do that in the structure over on the right as well. All these bonds are rotating, which means that at any given point in time, it's going to be a different carbon-hydrogen bond that's aligned, that's parallel with the MTP orbital shown to the right of the structure on the right-hand side of the page. So you also have 3 carbon-hydrogen bonds coming off of that beta carbon and this beta carbon and so on. Okay, now let's compare that structure to another one. So there's the carbon with the positive charge, And what we want to do is figure out what orbitals are involved in stabilizing this carbocation through hyperconjugation. So that's an alpha carbon, and one bond away are beta carbons. So it's any bond that's coming off of a beta carbon that you want to look at. So let's draw in the bonds that are not shown. So for each of those beta carbons, there's a couple of carbon-hydrogen bonds. And then each of these bonds is going to be associated with a bonding orbital and an anti-bonding orbital. So for example, over here, there's a CC bonding orbital, as well as a CH and another CH. And then we have the same situation on the right-hand side. So the orbitals involved in hyperconjugation for this structure, always going to be the MTP. So that's the one on the alpha carbon. And then coming off of the beta carbons, we have CC sigma, and we also have CH sigma. So these are coming from the beta carbons. Notice that this hydrogen here at the top of the structure cannot donate electron density. So there's no orbital attached to that hydrogen that would allow it to overlap in a parallel fashion with the p orbital on the alpha carbon. So along those lines, a tertiary carbon, a carbocation, is going to have more capability for hyperconjugation than a secondary cation, which is going to have more possibilities for hyperconjugation than a primary carbocation. So the order of stability of carbocations tracks with what we saw with the inductive effect on the previous page. Tertiary cations will be more stable than secondary cations, and those are more stable than primary cations.